Hello and welcome to another session in physics. In this session we'll be looking at the topic electric cells and electrolysis. But before that, let's review the previous lesson. Welcome back. At this point, let's see what we mean by electric circuit. Remember we said in our previous lessons, and we've been talking about electric current, and we said electric current is simply electric charge in motion. In conductors such as cables or wires, this current is made up of a swarm of moving electrons. Electric cells are chemical devices which allow electricity or electric current to flow through them. The electric force that is being produced in electric cells helps to push this current along. And if there is a complete circuit of conductors by which current can leave one terminal end of the cell and travel round to the other terminal of the cell, we say that a current will flow. So if this, for instance, is a cell, and then here we have the positive and we have the negative, and current can flow from here to here, then definitely there will be electricity. But for current to flow, there needs to be a force that will push this current up to this direction. Normally, electrons flow from the negative terminal or cathode of the cell to the other residual terminal or anode of the cell. Now, understand that if the conductor cuts at any point of this transmission, in other words, if there is a break in the circuit will be opened and current flow will be stopped or switched off. Now, electric cells are divided into two, namely primary cells and secondary cells. Primary cells are those cells that are able to stop working if the current in them has been used up. In other words, current is produced in them as a result of irreversible chemical change. Once they are used up once and for all. They can't be charged. But secondary cells are those cells which can be recharged by running current through them. We have about three components in a cell. For the primary cell, we have the two electrodes which are often made up of graphite, and we have the third item made up of the electrolyte. And for some other cells, we have electrodes. We have the positive electrode and we have the negative electrode. The negative electrode is called the cathode and the positive is called the anode. Though in some kinds of electrolysis, this position can change, where negative becomes anode and positive becomes cathode. Examples of electrolytes are aluminium, carbon, copper, iron, lead, and zinc. Electrolytes are substances, solutions through which current can flow. Now let's talk about the simple primary cell, known as the voltaic cell. The voltaic cell is created by placing two different electrodes, normally metals, inside an electrolyte. For instance, zinc and copper as electrodes. This is the cathode and this is the anode. Because of the depreciation or the decomposition of one of these metals, electric current will be made to flow. And on the voltmeter, you would notice a deflection, which means that the cell has created a voltage. If the deflection goes to the right, it means that the electrode at the right, or the anode, is connected to the positive terminal of the voltmeter. But if the reverse is the case, it means the cathode is the positive electrode. But if the deflection also is done to the left, what it simply means is that a reconnection needs to be done. So when you try to run a process of electrolysis, make sure that the deflection is always to the right, which shows that it is connected to the positive terminal of the voltmeter. Now, when it comes to simple cells, we have two major defects of simple cells, which are polarization and local action. Polarization refers to the release of hydrogen bubbles. When hydrogen bubbles collect at the positive electrode, it ends up insulating it such that current cannot flow through it again, and this eventually stops the working of the cell. This defect can be corrected by brushing the plate. Then in local action, it simply refers to the presence of impurities, which can actually lead to the gradual wearing away of the zinc plates, especially if the electrode, the zinc, is not always in use. It can be prevented by cleaning the zinc with hydrogen tetraoxosulfate and then rubbing it with mercury, which prevents it from coming into contact with the electrolyte. So this is an example of a simple Leclanche cell. So take time to go through this diagram and study it very well. Now, when it comes to simple Leclanche cells, we have two types of Leclanche cells. We have the wet Leclanche cell and the dry Leclanche cell. The wet Leclanche cell consists of a zinc rod at the cathode, the negative electrode, in a solution of ammonium chloride, which is contained in a glass vessel. The anode, on the other hand, is a carbon rod, and it is contained in a porous spot surrounded by manganese chloride, which works or serves as a depolarizer or helps to prevent polarization. So when an EMF in a Leclanche cell is set off by the zinc, the carbon and the electrolyte helps to drive current from zinc to carbon through the cell. Remember that the carbon is at a higher potential than the zinc, and this helps electrons to flow from the zinc plate to the carbon plate outside the cell. Normally, the EMF of a Leclanche cell is set at 1.5 volts. Some defects of a Leclanche cell, especially after it has worked for some time, results in the rate of hydrogen production becoming greater, which could result in the formation of polarization or the insulation of the electrode, which stops current from effectively flowing very well. So these primary cells need to be given rest from time to time. They need rest from time to time so that they will not break down. Alright, so for a dry Leclanche cell, one of the defects is heaviness, which also needs to be taken care of and given rest from time to time. One thing about the dry cell is that it can be carried about easily. As you can see here, these are examples of a dry Leclanche cell. The batteries we use in our cell are touch lights, our transistor radio batteries, and so many other appliances we use in our houses. But the problem with them is that due to local action, they deteriorate after some time. Daniel cell is another kind of a primary cell which is invented to counter or override the problem of polarization. The zinc rod in a Daniel cell is the negative electrode, while the positive electrode is the container itself. The Daniel cell is much more efficient than the Leclanche cell, and for this, it has an EMF of a constant value of 1.08 volts. Now let's talk about secondary cells. Secondary cells are of two main types. We have the lead acid accumulator and we have the alkaline or nether accumulation. Lead acid accumulation is the most common one that we use. When it is fully charged, its relative density and EMF are 1.25 and 2.2 volts respectively. But when it is discharged, it can be reduced to 1.5 volts and less than 2.0 volts respectively. So the raw density of the cell, in order to help it last longer, should not be allowed to drop to 1.15 before it is recharged. So it's not advisable to let it run out entirely. One way we can maintain lead acid accumulators is in 4 different ways. The first is that the liquid level must be maintained when we use distilled water. Also, the cell should be charged if its relative density falls below 1.15. It is also fully charged when relative density of acid is 1.25 and tested with a special hydrometer. The third way to maintain a lead acid is that if it is not lead acid accumulator if it is not in use for a very long time, it should be discharged from time to time or remove the acids and the cell dried up so that it doesn't deteriorate over time. Additionally, the battery should be kept clean so that current does not leak away from the casing between the terminals. Then about the alkaline or NECO accumulators, its name is gotten from the chemical symbol NECO and iron F, so that's why it's called the NECO or alkaline accumulators. Now this cell lasts longer and they are able to keep their charge longer, and they also require less maintenance. We see some of these cells in factories, in hospitals, even in some cars too. This cell is used. Even though they are expensive and bulky, with a small EMF value of about 1.25 volts, they are certainly worth the stress because they definitely last longer. Alright, so in summary of all the cells that we talked about here, it's important to note that we have simple cells, we have the Daniel cell, Leclanche, wet cell, Leclanche, dry cell, and the lead acid accumulator. At the end of this video, you can take note of your positive terminals, negative terminals, the electrolytes, and the corresponding depolarizers that they use. Now let's talk about electrolysis and electrolytes. Electrolysis, put simply, is a process where a liquid can conduct electricity through the movement of positive and negative ions within the liquid undergoing chemical changes. Electrolytes are the liquid themselves, which allow electricity to flow through them, and non-electrolytes are liquids which do not allow electricity to flow through them, such as alcohol, liquid paraffin, and sugar solutions. Okay, so let's talk about Faraday's laws of electrolysis. Faraday's first law of electrolysis states that the mass of a substance liberated during the process of electrolysis is proportional to the quantity of electricity passed through the electrolyte. Faraday's second law of electrolysis also states that the relative masses of substances liberated by the same quantity of electricity are proportional to their chemical equivalents. So these are some simple calculations that we have to do or carry out when it comes to calculating electrochemical equivalent of substances using Z equal to M over IT, where I is the current in amperes, M is the mass of the substance, and T is the time taken, while Z is the electrochemical equivalent of the substance. In industry, we use electrolysis in the electroplating of metals and the purification of metals and the electrolytic production of metals from compounds. When we talk about electroplating, we simply refer to the coating of cutlery and other articles with substances or elements such as copper, silver, chromium, nickel, or gold. And then when electricity is passed through a solution, we can notice that it reacts with silver ions by moving towards the cathode where they are discharged, and that is one way that a spoon can become coated with metallic silver in industry. Alright, when it comes to purification of metals, we, for instance, in the purification of copper metal, the impure copper is made the anode, while the pure copper is made the cathode. So when current is passed, copper ions are dissolved from the anode and deposited at the cathode, leaving the impurities behind. This pure copper is used in the manufacturing of electric cables because of its low resistance. Let's look now at electrolytic preparation of metals from compounds. Now, when it comes to the electrolytic preparation of metals from compounds, we have metals such as aluminium, sodium, and potassium. They are prepared from their molten chlorides or hydroxide through the process of electrolysis. Electrolysis is a very broad topic in physics, so do make sure to make reference to your notes one time or the other from the recommended textbooks for more information. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the tests that will appear on your screen.